Well, in section 6.1, we started out the prerequisites of probability and statistics. Now we want to do a second of our prerequisites and talk about the notion of sets and set operations. So in slide number 2, it lays out what we want to do in this section. We want to define and write sets in different ways. We want to be able to construct a Venn diagram, which is a picture that represents sets. And then we want to be able to determine the union and intersection of two sets, and then determine the cardinality of sets. All right, so we'll talk about what that is in just a minute. So in slide number 3, let's first define what we're talking about here. First, we can say that a set is a collection of numbers, letters, or objects. Many times for us, there'll be numbers involved. The objects are called elements, so the objects in a set are called its elements. Sets are named with capital letters. So you have a set A with a capital A, set M with a capital M, and so forth. And the elements in a set are enclosed in braces. So we'll write braces to, at the beginning of a set and at the end. And notice here the two common symbols for sets. First one, it kind of looks like an epsilon sign. It means is an element of. So you can say, for example, 3 is an element of the set A. So you'd have a 3 to the left of the epsilon sign, and then a capital A to the right of it. And if you do a strike through on that, it means is not an element of. All right, now in slide number 4, we'll talk about how we write sets. There's really two ways to do that. The first is the listing method, and that's where we simply list out the elements of what is in the set. And that's a good way to express ourselves with a set if the number of elements is fairly small. But if it's not, we have to have another way to do it, and that's with the set builder notation. So here, a typical element is named along with its description, and notice the example here. We could have B being the set of all X such that, and we say such that where we see the vertical bar, such that X is an odd number from 1 to 10. So notice there, those two sets we've written, A and B, are really the same set, right? Because set A has the elements 1, 3, 5, 7, and 9. Set B has the set of all elements X, such that X is an odd number from 1 to 10. So notice the flexibility in the set builder notation. I mean, what if that said odd numbers from 1 to 1,000? That would be too hard to write out, but we could do it easily using this set builder notation. Let's see. And finally, a set has no elements sometimes. And whenever that happens, we call that the empty set. All right, now on slide number 5, let's go talk about the first element of working with sets, and that's subsets. First, we can say if every element of a set B is also an element of set A, then we say that B is a subset of A. All right? So in other words, if all the elements in B are also in set A, we say that B is a subset of A. Now, furthermore, if B is a subset of A and there is at least one element of A that is not in B, then we say that B is a proper subset of A. In other words, it's a little bit smaller than A. All right? So notice the notation that we use. It's kind of like a horseshoe. For a proper subset, we simply use that sideways horseshoe. B is a subset of A. Excuse me, B is a proper subset of A. And up here, we have this same horseshoe on its side, and notice it has the little underline underneath it, simply meaning B is a subset of A. All right, now on slide number 6, let's start to talk about these operations that are associated with sets. The first one that's important to us is the intersection of sets. And notice what we have here written is called a Venn diagram, named after John Venn from Great Britain. So a Venn diagram is a graphical representation for the elements of sets. And we can say that for sets A and B, the set of all elements belong to both set A and set B is in the intersection of A and B. Now notice how we write the symbol for intersection. It's a horseshoe that's kind of written, that's upside down. All right. So an element is in the intersection of sets A and B if it's an element of A and also an element of B. All right. So let's say that again here. A intersect B is the set of all X such that X is in A and X is also an element of B. Now notice in the Venn diagram here, this blue area were these two circles that the first circle on the left represents set A, the circle on the right represents set B. That part where they overlap there that you can see in blue is the intersection of those two sets. And also note, if two sets have no elements in excuse me, if two sets have no elements in common, we say the sets are disjoint. In other words, their intersection is the empty set. It has no elements in it. All right. So the intersection of two sets is our first type of operation with sets. And then the next one is in slide number 7, the union of two sets. We can say here for sets A and B, the set of all elements that belong to at least one of A or B is the union of A and B. And notice the notation here, we use a horseshoe that kind of looks like a U. You can think of it that way. Looks like the letter U, A union B. So notice in our Venn diagram, the blue area here, think of the amalgamation of A and B. Everything in A, everything in B is in the union of A and B. And then down here in our set selector method, we can say that A union B is equal to the set of all elements X such that X is a member of A or X is an element of B. So if an element is in either A or B, it's in the union of A and B. And also the other note here, all the elements under consideration that we're talking about is called the universal set. And so that's why if you look up in your Venn diagram here, you see the U in the upper right corner. This is all the elements in the sets that we could be talking about. Sets A and B are specific here. All right, so let's start to take a look at some examples here and see how we do this stuff. In example 1, let's consider the sets A, B, and C.